Wissam, I see your point. I'm not sure if I want to start there or finish there, though. When you say mathematics is incapable of ontology, I really want you to tell me why would you hold that? I am of the opinion that mathematics is 100% exactly. It does the same work exactly as you do in a physical theory. So you examine evidence, and it's perfectly physical, and you have conjectures, and you go check them, and you do experiments. It's the same exact methodology. So if physics is capable of ontology, so is mathematics. But maybe we can leave that until the end, so that we we set the stage for that conclusion before we go there. You said last time we're gonna fight, so I'm ready for you. Anyway, so this is a continuation, let's say, of last week's room about the nature or the ontology of mathematics and its purpose and how do we know it works, etc., which is also related to the other room we did on induction. So we're getting there. We're trying to create this story of how is knowledge built and what do we know for sure, etc. So first of all, as usual, I would like to kick things out with everybody's favorite, the one and only, the most famous physicist, the second most famous after Einstein, Richard Feynman, on slide 2. He has these wonderful lectures. If you're not familiar with Richard Feynman, you should totally, if you're a science fan or a philosophy fan or both, you should totally listen to Feynman's lectures. Just beautiful stuff. This particular one, Feynman is talking about the difference between mathematicians and physicists, and mathematics and physics in general. It's part of a huge lecture, like it's a 1-hour lecture where he details this. I picked 3 minutes, which I think are the gist of his point. If you're familiar with Feynman, you will probably know the rest of it. But if not, I will try to summarize it in a nice table right after the video.
The mathematicians only are dealing with the structure of the reasoning, and they do not really care about what they're talking. They don't even need to know what they're talking about, or as they themselves say, or whether what they say is true. Now, I explain that. If you state the axioms, you say such and such a so, and such and such a so, and such and such a so, what then? Then the logic can be carried out without knowing what the such and such words mean. In other words, mathematicians prepare abstract reasoning that's ready to be used if you will only have a set of axioms about the real world. But the physicist has meaning to all the phrases. And there's a very important thing that a lot of people who study physics that come from mathematics don't appreciate. The physics is not mathematics, and mathematics is not physics. One helps the other. But you have to have some understanding of the connection of the words with the real world. And this is a problem which is not a problem of mathematics at all. Mathematicians also like to make their reasoning as general as possible. If you say, I have a 3-dimensional space, ordinary space, I want to talk about ordinary space. You know, you're in it, and you measure distances, and there are 3 numbers you need to tell where something is. You go breadth, width, and height. 3-dimensional space, and you begin to ask them about theorems. And they say, now look, if you had a space of n dimensions, then here are the theorems. Well, I say, yeah, but I only want the case 3. Well, substitute n equals 3. And then it turns out that very many of the complicated theorems they have are much simpler because it happens to be a special case. Now, the physicist is always interested in a special case. He's never interested in the general case. He's talking about something. When you know what it is you're talking about, that these things are forces, and these are masses, and this is inertia, and this is so on, then you can use an awful lot of common sense, seat-of-the-pants feeling about the world. You've seen various things. You know more or less how the phenomenon is going to behave. Well, the poor mathematician, he translates it into equations, and the symbols don't mean anything to him, and he has no guide but precise mathematical rigor and care in the argument. The mathematical rigor of great precision is not very useful in the physics, nor is the modern attitude in mathematics to look at axioms. Now, mathematicians can do what they want to do. One should not criticize them because they are not slaves to physics. It is not necessary that just because this will be useful to you, they have to do it that way. They can do what they will. It's their own job. And if you want something else, then you work it out yourself.
So, as you heard, Richard Feynman not only believes, as Wissam says, that math is not science, he believes that they are completely different domains. And he will detail his opinion in this lecture. He cites a little, some differences in the excerpt we listened to, and he mentions some more in the original lecture. In principle, before I get into it, to answer this question in principle, if I want to be very, very exact, if you follow me on slide 3, then I really need to be very careful and very accurate in defining exactly what mathematics is and exactly what physics is. I need to be absolutely 100% cutthroat in those definitions so that I can say, so that I can move to tackling the problem, okay, is mathematics the same thing as physics? Now, two things. Number one, it will turn out, and we will have another set of rooms around this. We call them demarcation problems. It turns out that defining exactly what science or what physics or what chemistry or what mathematics is not an easy task. In fact, it is a very complicated one. The other thing is we already discussed some of it in the previous rooms when we did induction and when we did the ontology of mathematics. So I'm not going to go into that. What I will do is I'm going to follow Richard Feynman, because Richard Feynman kind of details this very popular view. And I'm going to start with the popular view, and then we see where we end. Okay? Instead of starting at the complicated place, I'm going to take things as simply as possible. What I can do, though, without going into the specifics of demarcation, is if you follow me on slide 4, I can make this following table. Most people believe a version of this table. I don't want to strawman the argument. We're going to have a discussion in a minute about it. Let me just detail what this is for people only listening. So we will call, for simplicity, physics is the domain of investigation of the natural phenomena, right? And mathematics is the domain of formal reasoning and problem solving. This is what most people, this is the rough idea that most people have, right? And the differences between the two are very clear if you follow this view. So if you've listened to Feynman right now, you would notice that Feynman claims that physics is not certain, and we've discussed this with the induction problem, etc. But mathematics is certain when we spoke about deduction. Mathematics only uses deduction. Science or physics, let's say, uses deduction, induction, abduction, all those other forms of reasoning, other forms, other moves that are allowed. Mathematics doesn't use them. It's only a deductive science. I shouldn't say so. It's only a deductive method, let's say, right? Before I beg the question. Mathematics collects data, and this data is abstract, whereas physics collects observations. There is a natural phenomenon that I'm actually observing and I'm interested in, and those observations are not abstract, they are very concrete. I'm observing a very concrete entity in physics. I am using logical rigor in mathematics all the time. I have to mention the reasons, I have to mention the proof, I have to be very precise. Whereas physics, as Feynman says in this excerpt, sometimes physics just guesses the answer. It's not. He gives the example of Kronecker, I think, or Paul Dirac, or one of them. If you continue this lecture, in the same lecture, he mentions those, and he says, but they just guessed. They kind of just guessed what the equation is, and that's perfectly allowed in physics. Whereas in mathematics, according to the popular view, it's just not allowed. This is not a thing. It aims for general case theorems. We heard Feynman say, if you want the n equal 3, substitute it. So mathematicians want their theorems to be very general. They want their theorems to be very broad, whereas the physicist aims for very specific descriptions of very specific problems. And the last one I could think of is mathematics, and I kept it until the end for a reason. Mathematics considers any hypothetical situation. It's only limited by our imagination as mathematicians, right? Whatever you want, you can create in mathematics. Whereas physics considers and is limited to only one world, which is the objective, real, physical world. There's only one world that we're interested in. Whereas the mathematician can just swim in imagination all day long and invent whatever theories they wish. This is at least my version of the popular belief. I'm going to leave the mic open now for people to let me know what is it that they think is the case. Is it closer to their view? Is there something I missed? Just let me know. Let me just read in chat very quick. Some people were chatting. I must say it's not true that the physicist is only interested in the special case. Yes, Wissam, I absolutely agree with you. I'm going to go there. Yes, Feynman got that one wrong, well, that's my opinion at least. Feynman lectures on physics. Yes. Oh, he got us a quote. Mathematics is not a science from our point of view. Very nice. Thank you, Wissam. He says, mathematics is not a science from our point of view in the sense that it is not a natural science. The test of its validity is not experiment. That's according to Feynman. I think the computational crowd make a false equivalence between simulation and experiment. They even call them experiments. Feynman continues, we must incidentally make it clear from the beginning that if a thing is not science, it's not necessarily bad. For example, love is not science. So if something is said not to be a science, it does not mean that there is something wrong with it. It just means that it is not a science. So, slide 5. Point number 1. Again, we started with mathematics is certain. So that's the first thing. And physics and science in general is just not certain because of what we discussed last time, the induction problem and all that stuff. Remember this slide, we are on slide 5. Remember this slide, we showed it in the other presentation, the same one. And I'm gonna draw question marks around this certified seal. Because like everybody here accepts that there's uncertainty, right? Everybody here accepts there's uncertainty in abduction and induction. But in deduction, everybody presumes that there is certainty coming from somewhere. And of course, it looks more certain, if that makes any sense, than the other two, right? Because this is a deduction, it comes from the, it goes from the original, it goes from the general to the specific, etc., etc. It's a matter of definitions. Of course, we are sure of it. However, I do not believe this for the following reasons. What you see on slide 6 is an example of a proof. And I picked this exact proof because when we did a room a couple of weeks ago, like a friendly chat room, when we were talking about these things, I think Hiro brought it up. He was asking about the proof of the isosceles triangle criterion, which is if you have an isosceles triangle, it's enough to have two equal sides, so to have equal angles, and it's enough to have two equal angles to have two equal sides. This was proved in Euclid's Elements, of course. This is proposition 5, and this is an English translation with modern notation as well of that proof. Have fun, reading it at home. If you're interested, take a snapshot. Very clever proof, by the way. I must admit, this is not immediate. Like, this is genius. What I do want to do today is not explain the proof, because this is not a math lesson. But what I'm really interested in is to draw your attention to that certified seal, because this is math, right? That there's a certified seal, this is deduction, this is absolutely sure. And look first on those yellow marks that I have highlighted on the proof. The way deduction works, especially, back in the day, especially in Euclid's mind, is that you have to deduce theorems, we call them. So after you start from very given axioms or postulates, he called them. And he had something else called common notions, which we'll talk about in a minute. So using those, you can bring those together to start generating new truths, quote unquote, which we will call theorems. It's new things that you discover, And then this new thing is called theorem 1 or proposition 1, proposition 2, proposition 3. And then whenever you discover a proposition, you can use it to deduce the thing that follows it. So I am on proposition 5. I'm very free to use whatever I discovered before. So you see Euclid here referring to proposition 2. or postulate 2, or proposition 1.4, or you see here in yellow, in orange, I mean, CN3. This is common notion 3. Feel free on your own time to go back to Euclid's Elements and read what his 5 postulates are, and read what the common notions are. Things are equal to themselves, and all the right angles are equal. And his 5th famous postulate that makes no sense. It's just very complicated language that we kind of translated in different manners, etc. This is not my point again. My point is, if we're looking at these things, what if the proof of one of those things had a mistake? So the proof of proposition 5 relies on proposition 1.4, proposition 1, proposition 1.3, postulate 1. What if something is wrong there? What if I am at theorem 85? Can you absolutely guarantee that we haven't missed anything? What if nothing is wrong? What if nothing is wrong, but instead of writing postulate 2, he wrote postulate 3 by mistake? So he's referring to the proof is perfect, but instead of writing postulate 2, which is what he wanted to write, he wrote postulate 3 by mistake. This ruins the entire proof. This makes the piece of proof in front of me wrong. If I'm a math teacher, and I am, and someone writes the wrong name for the theorem, you know, as they refer to it, it's not like they have to memorize it, no. But as they refer to it in their work, they wrote a different theorem than the one they want to refer to. This proof is wrong. It's just not the case. That postulate 3 does this. Postulate 2 does it, yes. So there's a mistake. How can we be sure? Well, we send it to another mathematician to certify it. Okay, what if that other mathematician also doesn't certify, but did not find the error? So that's problem number 1. We can never know that what is in front of us on the paper is absolutely 100% deduced correctly. We have to sit down and check whether this deduction is correct. Just checking for typos is enough to ruin. Just one typo in this whole thing is enough to ruin the entire thing. Okay? Problem number 2, from the same spirit. These common notions that you use, who says they are common? Common where? Common relative to whom? Do we have to pay and agree to your common notions before we get in? Okay, fine, we agree, but you're asking us to pay beforehand. No, this doesn't work. When you want me to agree with you on something, we have to start in the same base. Starting at the same base does not require me to agree to every common notion you postulate. The feeling of, imagine a mathematical system that says everything I will tell you is an axiom now, to show you where the problem is, because of course we have to agree on certain axioms to start. But imagine a mathematical system that says these 300 lines, they are all axioms, and that's all I want to tell you. These are axioms. My opinions about this theory are the axioms, and you're not allowed to logically speaking, you're not allowed to object because they are common notions, quote unquote. And how do we where is the okay? Oh, so now you have certainty because you forced my hand into agreeing onto these common notions. Wow, very intelligent. Like, this is very useful. Where is the certainty? I'm not questioning the fact that we have to agree to axiom. I'm just questioning the fact that, people give in to this feeling of certainty that mathematics gives. It's not. It's paid for. We paid for that certainty, and you pay with the price you pay is you have to agree to common notions and axioms that you probably don't want to agree to, or you have other reasons not to agree to, or you just think they are weird. Just like Euclid's 5th postulate, for example. People later on thought it's kind of weird, this postulate that he uses, and they started using others, and they have new theories now. They have other geometries which are arguably more useful if you want to talk about the usefulness. So this is Euclid. This is a very old mathematician. This is very classical. Everybody knows the geometry. Everybody knows the proofs. Everybody's comfortable with it. We all studied it in school. Then you will tell me, okay, modern mathematics is different. Modern mathematics has axioms and has logical language, and it doesn't use natural language like Euclid did. He wrote in Greek. Well, probably he and his disciples, but that's a different discussion. We're reading an English text, typos could ruin it. Okay, fine. Let's go to the hard logical math, right? Let's see a modern example so that we know, right? If it is mathematics wasn't certain back then, let's see if it's certain today. So on slide 7, we see the story of a very famous man, one of the most famous mathematicians alive today. If you've heard of Fermat's last theorem, you know the guy. This is none other than Andrew Wiles, the legend, who solved the problem that stayed for 400 years unsolved, despite the fact that it's a very easy problem. Okay? In short, this is the generalization of a Pythagoras theorem. So instead of having x squared plus y squared equals z squared, which is the Pythagoras theorem, which we know that has infinitely many solutions, Andrew Wiles proved that there are no solutions in integers for higher powers. So for power equal 3, power 4, power 5, power 100, power 1000, you cannot find integer solutions for these equations, unlike the case for Pythagoras, which you can find infinitely many because they turned out to be right triangles. Anyway, this is the story of quote-unquote certainty of this proof. So why is it called Fermat's last theorem? Because 400 years ago, Pierre de Fermat, a mathematician, was reading a book on arithmetic. And he started making comments on this book, on this manuscript he had. Now, his disciples, probably from his children or something like that, I'm not sure of the story anymore, but that book ended up being famous because all those annotations that he made on the side of the book, they had guesses. And I'm saying guesses because he never proved anything. Sometimes he would manage, to write some intuition. Sometimes he would very rarely, he will take the time to actually prove it somewhere else in a different place. But on the book, he just had guesses. But guess after guess after guess, people started proving them. So it turns out that he was making very good guesses. What are they? What is he making? The mathematician guesses. 400 years ago, we're not judging. We are modern mathematics now. He makes these guesses, and he makes one of those guesses is what we call today Fermat's last theorem. Xn plus yn equals Zn has no solutions for n equal 3 or higher. Fermat himself claims he has a proof. He writes the famous joke, right? I have a proof, but it doesn't fit in the margin. And then separately, later on, he proved the case for n equal 4. So for the power 4, he managed to generalize it from Pythagoras. So using some relation to Pythagoras, he proved that it's not possible. And then 200 years later, another mathematician, brilliant person, Sophie Germain, she proved the case for n equal 3, n equal 5, n equal 7, which turned out to be very expensive. And then Ernst Kummer, very modernly, I think, 50, 60 years ago, something like that. More actually. Wait, I'm too 120 years old, something. Anyway, he proved it for all regular primes, right? So if you're not sure what regular primes are, this is a family of primes that is related to this problem. Just click on the link if you're a nerd and you want to find out. Not very important. So until now, we don't have a proof, but people are still guessing, and they're saying, oh, no, that still doesn't have solutions. Start working on it. All we have is guesses and then proofs for very specific cases. The computer gets us to 4 million. So when the computer age started, we started running these numerical methods to solving this. And it got us up to 4 million. And then some other developments happen as well. And then we reach the place where Andrew Wiles, the famous mathematician, started working on it. He spent like 20 years of something working on it in secret because he was too ashamed to admit that he was working on the problem, because everybody called him crazy for working on it. This is a famously 400-year-old, notoriously difficult problem, right? He ends up connecting and inventing all sorts of new, very modern, very, esoteric mathematical theories, I want to say. Something that has to do with also developments happening in Japan in parallel. He publishes a proof in year 93. Sorry, I'm taking a whole lot to tell the story, but this is the story of certainty, I remind you. Huh? All of this is very certain, absolutely, 100%. He publishes a proof in year 93. An error was found as they review the proof in year 94. He spends like 2 or 3 months thinking about this on his own, doesn't get anywhere, gets the help of his student, Taylor, they sit down, work on it for 7 or 8 months, and then they publish a correction in year 95. And then after that, people visit it again, and they're like, okay, everybody now is happy that Andrew Wiles has the proof. It has been established for around 30 years now that Andrew Wiles, in the second attempt, he got the proof right. This is the story of mathematical deduction and certainty, from Pierre de Fermat to Andrew Wiles making the mistake on the first time. Just to show you again that even with modern mathematics, super esoteric, super precise, super careful, you can still make mistakes. What does this look like to us? Does it look like certainty? Does it look like this method autocorrects? Well, if it does, I have news for you. The scientific method does exactly the same way. People have guesses, they go, they experiment, they refine them, the scientific community looks at them, they find problems with them, they fix it again, they publish, someone else fixes it, someone else uses the result, they come up with something new, etc., etc. Just by judging point number one, they look very, very similar. In mathematics, it is the mathematician who is responsible to check for the validity of their work, and it is up to us to trust or not trust the rest of the community. And then when a community of mathematicians says Andrew Wiles has it right, it's not up to me to tell them no. I don't know. I must sit down and learn the theory myself. To be frankly with you, I haven't. This is way above my pay grade. And it's above the pay grade of most people. And when they said that there was a mistake, we all believed them. And then when he published his first proof, we all believed, oh, he has the proof. And then when they told us that they don't have the proof, we believed them. And now we believe them. We're taking them face value. Just like what the doctor says. The doctor is the product of all of this history of scientific method. He comes down and he gives you this pill. You know, for 3,000 years of medicine, the good, the bad, the ugly, right? The trial and error, all you want. They give you this pill and say, trust me, this will heal your headache. This will heal your diabetes. This will heal your whatever. And you take it. Same exact thing. This is the story of certainty in mathematics. This is point number one. I go back to the table to make the point, to show you. Point number one, I want to remove certainty from the equation. Both mathematics and physics are not certain. They are up to us. We check for validity. We are fallible. Therefore, there is no way I can trust the work of any human being. If it is up to the mathematical community to check for people's proofs, it is up to the scientific community to check for people's proofs in science. Same exact methodology. I will leave room for your questions now. Just about point number one, if you please. So, and I want to hear if people have other opinions, of course.
Well, I think that's really nice. I mean, I like it's the element, it's the sense in which mathematics is like physics. The proof becomes the thing, and it's the proof itself becomes the thing that might be wrong rather than the theory, right? I mean, Newtonian mechanics, Newtonian gravity makes wrong predictions. Maybe I should say, when I say that it makes wrong predictions, we've agreed on the fact, like for instance with Mercury, we've agreed on what Newton says Mercury's orbit should precess, and we observe that it doesn't. And so Newton is wrong. Well, maybe we didn't measure it right, or maybe we didn't calculate what Newton's theory says. And I know I haven't checked either of those things. Both the measurements and the theoretical prediction using math and Newton's laws are incredibly complicated. And I'm taking people's word for it that they don't agree, and therefore Newton is wrong. And so in a sense, that's I mean, I really do like that even in math, you have that community, the consensus of the mathematical community is all you can really depend on. And I think maybe that's what you're saying.
Of course, and I'm going to even give you more before I go to Wissam's point in chat. I'm a math teacher, right? This is what I do. You're a physics teacher. Okay, you can be a language teacher. You can be whatever you want. In your classroom, You are the authority, essentially. If someone brings you a piece of work, even though it is correct, and it has happened to me, and I'm pretty sure it has happened to you and to every person teaching out there, sometimes you get fooled. You look at work and you say, this work has mistake. And then the student has enough courage to come to you and tell you, I don't think you've corrected my paper in the right way. I think you've made a mistake. And then you start debating, and then you discover your own mistake in the classroom. The student will correct your own mistake as the expert. And then I ask myself, okay, of course, I'm very embarrassed, I'm so sorry, etc. But then I ask myself, how many students are too shy to ask me whether I miscorrected their papers? How many write proofs that had brilliant ideas, I was just too classical not to see? And then in that classroom, I am the scientific authority, I am the community, right? But even if you bring 10 mathematicians and they look at this paper and they didn't find the mistake, or they found a mistake that is not there, both false positive and false negative, what happens? Nothing. It's their word, right? It's their word that will go. And if you keep generalizing, then you will reach to the entire scientific or mathematical or physical or whatever it is the domain that we are talking about. And of course, the more you get complicated in nature's phenomena, the more different opinions you will find. So if you go, for example, to neuroscience, or if you go to psychology, or if you go to sociology or to politics, you will see experts fighting to death because they have different outlooks. And it doesn't mean that those outlooks aren't quote unquote valid in certain frameworks. It just means that science hasn't developed quite enough to be, I'm running ahead of myself here, as stable as the system we're dealing with, which is the mathematical system. Enough about this. I'm gonna talk about this later. But of course, if you imagine this small example in the classroom and you generalize it, I think it's the exact same thing happening.
It does strike me, though, that the difference that I see between math and physics, for instance, is that in math, the lack of certainty comes, I think, only from the fallibility. You have these premises, and they do lead to certain deductions if the proof is right, and that's at the end of the story. In physics, the deductions based on the model can be exactly right, but it may not agree with reality, because it turns out it's not because you've made a mistake,
Oh, we're gonna get
other
there.
than the fact that your model is wrong. Yeah.
Yeah. I'm gonna get to the measurement bit where the stuff that is error in the experiment and error in whatever, it's coming. Wissam, rebuttal to point one. Many domains in life share this quality. This is not an argument for equating them. Absolutely, 100%. This is just one row in my table, right? So this is point number one. People believe that mathematics is absolutely certain, and that's how they will differentiate it from doing physics or other sciences. I'm saying point number one fails for now. Of course, this is not by its own an argument to equating them, but hopefully by the end of today, it will become a little bit more closer. I will move to point number two. I will group the second, the third, and the fourth row in one example or one discussion. So mathematics is based on deduction only. Mathematics collects data, and this data is abstract, and it uses logical rigor, versus physics that uses deduction plus induction plus other forms of reasoning. It collects observation instead of data, and those observations are concrete physical entities. And it sometimes guesses the answer, so no logical rigor whatsoever is necessary. I'm going to combine those three into one discussion. Slide 10. Consider the first 300 prime numbers. They are on your slide, and I have included the name of the sequence here. If you want to refer to larger numbers, you can go click and watch this for yourself. These are the first 300 primes. If you look there, you will see some things colored in yellow. Okay, you have no idea what this is. This is just a list of objects, and you have these things colored in yellow, and then you look here and you say, oh look, between 3 and 5, there's a minus 2. And between 5 and 7, there's a minus 2. And between 11 and 13, there's 2. And 17, 19, there's 2. 29, 31, there's 2. 51, 59, 61, there's 2. 107, 109, there's 2. And so on and so forth. These pairs keep occurring. We call them twin primes. Essentially, primes that are neighbors. They are twins, they call them, because they have a difference of 2. And guess what? There is no proof. Is there any valid proof of this? No. Anywhere? No. Any suggestion? No. Any let's say, submission of a proof. So someone thinks that they have a proof and they've submitted it, and we are reviewing it. So that to check for validity or not is a different issue, right? Oh, we have, just like Andrew Wiles, we have a suggestion of a proof, and then we're going to review it, see if we agree or not. No, there's nothing like that. This is just a twin prime conjecture, we call it. A conjecture is a result in mathematics that looks to be the case. Okay? Point number 1, we said mathematics does not collect observation. Can you tell me exactly what this is? What is it that we've done now? This is exactly what observation is. You have a list in front of you, and you're looking at this list, and instead of just looking at the list, blindly, oh, it's a list of increasing numbers, that's data, right? Oh, you're looking, oh, I'm observing, I don't want to say meaning, but I'm observing relations between objects on this list. This is exactly what a physicist would do if they're observing something new, or a chemist, or a biologist, or it's a new phenomenon. This is the list of primes, and I just paid attention. It's been in front of me for decades. It's been in front of me for millennia. The solar system existed ever since we did, and even way before us. But we just started, in history terms, right? Yesterday night, we started discovering what's in the solar system, relatively speaking. So this list of primes was in front of us as well, all the entire time. But then at some point, people paid attention that, oh, look, there's this 2 difference between these 2. And it looks like it goes on forever, as far as we can reach and calculate. So the claim that mathematics does not do observation, I think, is misleading. This is exactly observation and the conjecture, just like the scientist does. Observation, hypothesis, and then you go test it. Exactly the same thing. We will talk about the test later on. Let's take them step by step here. The claim that says mathematics does not collect observation is mistaken. At least some mathematics. Some other mathematics could not use that, right? But some mathematics clearly does. If you want to call the twin prime conjecture not mathematics, I have bad news for you. There's tons and tons of those examples. The Goldbach conjecture is one of those. The Fermat's-Last theorem we just saw is one of those. You can go on forever. So if you want to discard all of those as not mathematics, then this is up to you, but I'm not of that opinion, and I don't think you will have a lot of friends taking that side. Calling everything that only has proofs that were validated by the mathematical community as math, and everything else is just not math. So what does the mathematician do? They do nothing until they have a valid proof that everybody agrees to. No, I don't think people will agree to this. Just like people who do science are always on the edge of the discovery. It's not always, me explaining whatever people have discovered. The real scientists, what the scientific method is really needed for, is not for the established things, it's for the unestablished thing, it's for the edge. And this is exactly what we need, methods of discovery in mathematics, quote unquote discovery. Because I say discovery, we haven't shown the entire argument for it yet. This is exactly the same exercise. This is point number 1. When you say science guesses the answer, that Feynman says, oh, it's enough to guess the answer, but mathematics never does. This is exactly what we did. We're guessing the answer here. What did Andrew Wiles did? He guessed the answer. What did Euclid did? He drew some circles, he drew some triangles, and he says, you know what, this looks like the case. Let me try to prove it. So this is guessing. This is the same exercise, absolutely the same exercise. There's no difference between this kind of guessing and the other kind of guessing. Number 3, when they say mathematics is abstract, and then the other observations is concrete. What's abstract about this observation that we've done? This is a very physical list in front of me of objects, and those objects have properties, and I am remarking their relationships. I'm remarking those properties. In what sense is this different from observing something fall down in the physical world? There are two objects, the planet Earth, right, if you want to take the Newtonian sense, and then another object, and these two objects are interacting. They have a property that they attract each other, and I'm observing that property to reveal its shape and let's say its details. I'm doing the exact same thing here. I have objects, and these objects have relations, and I'm kind of observing, making a guess about what the real details of those relationships are. In what sense is this abstract? Nothing abstract about this at all. Just taking this, yes.
I'm trying to think. So I just talking about the twin prime conjecture, right? You look at it, you say, okay, I'm going to guess that they go on forever. And that is very much like physics. I'm going to guess that masses attract masses, and with this formula, I think. Can I just thought? Yeah. Is that a fair analogy?
In my mind, it's the same kind of activity, right? They might differ in the method used. They might differ in the observation criteria that you use, which is something we're going to get to. But for now, I'm just asking the abstract business. I'm just asking whether the guesses happen or not, and I'm asking about the deduction. That's what I'm asking about.
No, I think it's really a good example. It makes me appreciate that there are things in math that we haven't proved. We guess. We actually guess at a relationship that we can express that we can't prove, and that's exactly like what we do in science. But I wonder about this possible difference in that, for instance, in the case of the twin prime conjecture, I don't see any entailments of that I can use to falsify it, other than the fact that you'll never see twin primes. And in science, you come up with a guess. That guess has all sorts of entailments beyond just, oh, but here's a mass that doesn't, if I see masses attract, or I think that's what's going on, I could observe a mass not attracting another mass. But there's lots of other ways of falsifying it because the entailments go on. And I don't know if there's a difference. Maybe you can convince me.
There's no difference. It's just that you and I don't know enough math. Sorry to jump in here immediately, but
So what do you mean? So you mean there are
what do I
entailments
mean? I mean this twin prime conjecture.
Yeah.
I'm gonna make it easy. When I say I want a proof of the twin prime conjecture, what is it that we're looking for? I'm looking for a list of statements that, linked with derivation rules, are going to get me to the twin prime conjecture. This is what I'm looking for. These theorems are already the ones I'm using. Some of them are axioms, so we all agree on. Most of them, actually, at this point, instead, the vast majority of them should be discovered theorems. And I'm using the word discovered more and more now. So now when you say I don't see the relation between the twin prime conjecture and other theorems to see whether there are entailments of this or not, you and I don't know enough math to say this. I can tell you immediately that this twin prime conjecture is linked to the Riemann hypothesis. It's linked to the Goldbach's conjecture. It's linked to all these things that we still are trying to discover. So proving one of them can make easier proving others, and disproving one of them can make it a lot easier to disprove others. And this is exactly how Fermat's theorem was proved 400 years after its conjecture.
Yeah. Okay. So that's right. So I guess I see possible linkages, entailments, things that you could disprove something else and therefore disprove this thing. But as you said at the beginning, what you're looking for is a proof of the twin prime conjecture, and that would be like looking for a proof that masses attract other masses. Nobody thinks that's possible.
Or a proof by contradiction. Unless you are an intuitionist, if you remember last episode when we said there's a camp that refuses the negation of negation is not the thing itself, so they refuse the excluded middle rule, etc. But if you are a classic logicist, we accept at least the majority of them. They accept the middle third removed rule. So that now, if either I can find a direct constructive proof of the conjecture, like a direct, either a constructive proof or an entailment of that conjecture by other theorems, or I can say, let's assume this doesn't work, and then find the contradiction you're asking about. So when someone finds that contradiction, then they have proved that this is not the case, or they have proved that it is the case by proving the negation wrong. Does that make sense?
Well, I'm not sure I followed all of that, and maybe just tell me whether you a simpler way to address this. In the case of the twin prime conjecture, it's completely conceivable that you could prove that that's true, and people would agree that the proof is valid and all that kind of stuff. It's inconceivable, I think, that you could prove that masses attract other masses.
The word proof, I only understand in one meaning, which is entailing from given axioms. Now, I can do it in two ways. I can cheat and say masses attract other masses as an axiom, which is kind of what physics does. I'm not sure. You correct me. Is it not very analogous to when you say, oh, there's 4 fundamental forces in the universe, and gravity, at least in the classical sense, used to be one of them? So you can't ask me why is it that positive charge attracts negative charge. It just does. I just use that fact to explain everything in the universe. You can't ask me why masses attract. This is the property of a mass. This is exactly what we understand mass as. So there's that thing. Or I can start from other givens, which is kind of what, if you remember back in the day, I sent you a paper of axiomatization of relativity, special and general. So they started from other givens and then they entailed all the others. So this is the sense of proof I understand. When you say it's impossible to prove something, at least in the banal, naive sense, I can include it as an axiom, and that's enough proof for me. You know what I mean?
I wanted to answer your question from the words of Leonard Susskind, who recently said quite simply that string theory is not a description of the universe we live in. Now, I think that a description of the universe we live in is the proper definition of physics. And string theory is certainly math, but it is not physics, according to Leonard Susskind.
Just
I
for the
have,
record,
yeah.
I agree with that.
I have no horses. I have no horses in that race. I agree too. Whatever you want to call physics or not, again, we're not about the demarcation here. Although it is very essential part of the discussion, I cannot tackle everything at the same time. All I'm saying is there more similar? Let me not say more. Now people will catch me. They say he's going. Are they the same exercise? So when I'm doing math on a piece of paper and when I'm doing physics exploring the universe, are they the same exercise qualitatively in logic, in shape, in practice, or is there more in physics than there is in math? And this is what we're discovering here. And I give you back the table of what we have discussed so far. So people usually claim that mathematics is certain. Turns out it's not the case. People usually claim that mathematics only does deduction. So no induction, no abduction, no observation, no nothing, no collecting data, no using, guessing. We only use logical rigor in mathematics. Turns out to be absolutely not the case. And we used examples from the history of mathematics, modern and old, to show that these things continue to happen right in front of us. As long as you are, you're not willing to claim that everything that doesn't have is not mathematical activity, you will not have friends with that opinion. I cannot argue against you. You are, but this is very extreme. I don't think that mathematicians who are working in their research now are not mathematicians simply because they're trying to find a proof. I think this is exactly where the real hard mathematics happens, not in my classroom when I'm teaching, beginners. As far as we can tell, those presumptions about mathematics are kind of looking shaky, let me say. In my mind, they have already fallen, but I'm hoping that in your minds, they're kind of starting to look shakier than they were before. Any last thing about these 2 points before we move on? I still have a couple, and then we can open a general discussion if you like. I want to apologize to Wissam. I wasn't looking on chat a little bit ago, like 30 minutes ago. I'm doing a lot of things, so please bear with me. He says the tarot card reader observes their cards. You are right that mathematicians also observe things, but we still lack an argument for equating these things. Absolutely right. Just based on that one point, because the observation happens here and there, doesn't mean that they are exactly the same domain. we are running through the phases of, let's say, similarity one after the other, and they're gonna start falling one after the other. The differences, and they're gonna start to fall one after the other, and hopefully by the end, I will get to every point you have in mind. And if I don't, then we can talk about two more points that Feynman himself mentions. Mathematics aims for general case theorems, as general as possible, he says. And then physics aims for very specific results. The physicist doesn't care about all the objects in the universe, Feynman says, but the physicist only cares about the situation in front of her or him. This situation, I can describe it by guessing, by deducing, by inducing, by whatever you want to do. Can I describe it faithfully? Yes, then I have done my job, irrespective of all those other phenomena happening over there. And if you go to a lab, a proper lab, people take huge care in isolating that lab from the outside universe. They wear triple coats, they wear gloves, they wear masks, they bury it underground just to isolate all those variables. I only want to observe this one thing. I don't want to observe the entire of the universe. That's too complicated for me. I don't want to worry about all those. I want to isolate all of those so that I can observe this one thing that I really care about. That's my job as a physicist. Whereas, according to Feynman and many others as well, mathematics does the opposite thing. The more general the situation is, the more general the discussion is, the better for mathematicians. Okay, let's tackle that one. Let's see if that one holds. It's enough in my head to provide two counterexamples, one for the first and one for the second, just to show, just like we did previously, just to show that even though sometimes things work in that way, many other times things don't. For mathematics, I'm going to give you this dumb logic that I have created. If you are with me on slide 13, I'm going to define one variable only, x. I'm going to define one constant only, which is a. Okay? And then I'm going to set as an axiom, only one axiom, the dumbest logic you can think of, only one axiom, which is that a is entailed, and only one derivation rule, you can see it dr there, which says any variable entails a before that variable. Just a simple concatenation logic. And then what are the theorems? Well, a is a theorem because a is an axiom. And then from a and the derivation rule, I can deduce double a because a before the variable, and then if you substitute the variable x with a, you can get double a, and then you can get a triple a, and you can get quadruple a, and then you can continue this. You can continue generating theorems here. Any one of those, you can publish them and say, I'm a mathematician. This is completely fine. Either this is math or this is not math. If someone wrote this on a piece of paper, would you say this is math or not? I say this is math, because if it's not math, what is it? Is it not mathematics, the art of deduction and formal reasoning, etc.? This is it. You want something more complicated? You want more arithmetic? I can add all the axioms of piano arithmetic for you. You want set theory? Oh, by all means, we'll add it. But it's the same exact work. It's the same exact work. If this is the case, we are not discussing this. We're discussing the claim that mathematics always aims for the most general case, the most general theorem. But look at this example. This example is so specific, it's actually useless and meaningless. It's so specific. Can you think of one thing that you can apply this logic for? One thing, just one situation in the world, in your imagination, anything you can. It's so dumb, it's so useless, this logic that I have created. Where is the most general case? And you're going to say, oh, but this is a dumb theorem. This is a dumb logic that you created. The good mathematics is the general case one. I'm sorry, number one, who says who? Number two, all general results start as very specific. We just saw the example of Fermat's last theorem. It started with someone proving n equal 3, Fermat himself proving n equal 4, Sophie Germain adding 3, 5, 7, someone else adding whatever family of primes, someone else. They start as a specific thing, and then they walk to the general. And this is, of course, desired. This is always desirable, having one small result in my pocket that explains a lot of things. This is very reasonable to look for. But can I claim that the people who did the work for specific cases are not doing mathematics simply because mathematics always aims for the general case theorem? No, I'm not willing to make that claim. So even my dumb logic here qualifies. Is it not an art in deduction? Is it not formal? Is there anything here that is not defined? No. Same thing for all the other theories in mathematics. You want the general case? Of course, everybody wants the general case. But if you're working in a specific case, doesn't mean you're not doing mathematics. So this point is highly questionable here. This position by Feynman is, I find it odd actually that Feynman himself makes that claim. The other face of the coin, physics. Physics in Feynman's mind aims to describe very specific phenomena. Just give me the description of this one thing I'm observing. Don't bother about everything else. I have a rule here in physics, at least in the classical physics, right? But I'm sure we have physicists in the room here. I'm sure that all the other developments in physics cannot go away from this one, and we can have a discussion about this, why or why not. But we have a very simple rule here. So this is the action-reaction rule, third rule of Newton. Whatever force is applied from A to B, there's an opposite and equal force applied from B to A. And this is kind of, if you want to think about it, one of the axioms, one of the definitions, one of the whatever that Newton does. Either you can think of it as a theorem that could be deduced, or you can think of it as an axiom. Not my discussion now. My discussion is on that specific point. Is this a specific description of a physical phenomenon, or is it the most general thing you can think of? This law, does it apply to one kind of forces, to one force in particular, to one experiment in particular, as Feynman posits that physicists always like this? Or does it have a more general, the most general form of validity, let's say, of description? This is used everywhere. There's four fundamental forces, classically speaking, in the universe, and all of those forces they obey this. And then you can derive more families of forces. Let's say, contact forces, they're kind of a version of electromagnetic. Whatever, it's a version of the. You know what? You can always add more or less forces to that set. But all I'm saying is this rule applies to all of them. Is this not a general result? This is the most general you can think of. So again, the point that he makes that physics only cares about particulars and then mathematics always cares about the general is not always the case. I say generality and having a very general rule, just like we have F equals MA, or F of A over B is the minus of the other one. These are very nice to have, just like it's very nice to have a result about all real numbers or all complex numbers or all Hilbert spaces or all spaces in general or all logics in general, whatever. It's always nice to have one rule that describes many, many, many things. It's economic. We like these, whether it's in math or in physics. And we always, I shouldn't say always, but most of the cases, the vast majority of the cases, all of these general rules, they have started as very specific observations, whether it is in mathematics or whether it is in physics. Someone notices something, they wonder what is the scope of that observation, and then they start creating the necessary theoretical framework, whether it is in math or in physics, to kind of describe it and derive it. Questions? Or comments or whatever.
Well, so I'm still just struggling, the basic thesis here, because primarily because unless it does get down kind of to the question of does this stuff exist and we're discovering it, or are we just making it all up? And I guess I know this is kind of simplistic, but I'm thinking about in math, we do make some postulates. That's all we can do. There's nothing you can do but make postulates, and then everything flows from them, with the exception of human fallibility, in a perfectly logical way. I mean, yes, I think the element of human fallibility does inject some interesting similarities, and it draws the question of what is consensus in both math and science. But ultimately, once you have decided on postulates, that's it. I'm saying you can't ask the question, are the postulates wrong? They're just postulates, and everything follows in a very certain fashion. There's no questioning any of that. Whereas in science, the example that you give, Newton's third law, is not a I mean, it turns out there's all sorts of cases where you see it's violated, and then you see you can fix it by changing the definition of force or by doing something else. but but fundamentally, the thing you wrote down was a guess about reality, and it can be falsified. I mean, it can really literally turn out that that basic postulate is just wrong, and that's just not true in math.
Uh, I'm not sure whether I should reply from the physics point of view or from the math point of view. I think we will meet in the middle, but let me try from the math point of view first. There was a movement. Prime numbers have been an obsession for the entire history of mathematics. There was a movement to try to predict a formula for the primes, and it still exists for today. Like, people are hunting for this forever, and the current belief is that this is random. Until you find the formula, of course, the current belief is that is that this is completely randomly distributed. When you say completely randomly, we have some idea that it is also not the case. So people have discovered that primes are becoming more and more scarce. So you have to go through a lot more numbers the larger the number is, so that you can find the second prime. One of those developments, it was Gauss and someone else, I forgot really the story now, but they have conjectured that, I think Gauss and Riemann, and then as a joint work, don't quote me on the story, but they have conjectured that prime numbers are approaching a certain limit of density. Okay, so it's always less than or equal than the log of n over n, or something in that order. I don't even remember the actual. It's not really important. And then the only way you can verify this, John, is not by doing some rigorous deductive proofing, whatever. The only way is, if you want to measure density, you have to have a big set of numbers and then divide the numbers you care about over the total. It turned out that it took a long time so that we can collect this. Of course, we didn't have computers, etc. And it was later on discovered that the actual number is above that limit that they did. So after like n equal 4 million or something, it goes above. But then they discovered that it goes below again. And then they discovered it goes above again. And then they discovered it goes below again after a certain n. And then the theoretical proof came that, oh, you know what, this is a limit, at infinity they converge. After that point. Okay? If you have a problem with that, how should I phrase this? That activity, in my mind, is the same exact activity that you are doing when you say, I don't have a proof in physics. When you say, I'm changing the definition of force, why would you change the definition to make a certain thing work out? Because of your personal preference, because you want this preference to help you deduce things, right? You're kind of tweaking those axioms because you want to prove a certain thing. You're begging a certain result that you are observing. That Gauss and Riemann were also doing the same exact thing. You can tell me now, oh, they did not change the axioms. Oh, they didn't. But how did we get, for example, another branch of mathematics, which is non-Euclidean geometry? We changed an axiom. Is this making sense to you?
Yeah, right, and we're back to the example, right, of the twin prime conjecture or anything else, and I really do like that. I think within math itself, there is an activity that is like physics, like I described in physics. You make the twin prime conjecture, and it can turn out that that's just not true. That there is a place where you stop getting them or something, whatever the violation would be. So
And
that
that's enough,
is true.
right?
Yeah,
And
no, you're
when
right.
we
I think
discover that's enough for us to. I don't even want a proof of the negation. You know what I mean? I just want that one specific counter example, and then I'm happy. Just like the same thing as in physics, the same exact thing.
well, I think you're right. I guess the difference is math starts with somehow there's a starting point that's different. The starting point of all the proof that the twin prime conjecture is wrong would start with, an understanding that the rules of math are the rules of math, right? I mean, the fact that the conjecture is wrong is stems from an acceptance of fundamental ideas in math that you can't you don't get to question. Those are just, they can't be wrong. They can just be, not your preference to choose them. Whereas in physics, there isn't anything at the base. There's nothing at the base that you can be sure of.
I,
Nothing.
I wholeheartedly disagree with that. I think this is kind of not how to say. This is ungrateful of physics to say this about, because you guys owe the mathematical development quite a lot. When you say I don't have to assume anything, there's no base. Oh, the entirety of the body of mathematical theories is already assumed with you, plus the body of theories we will talk about in the future, which is the scientific method. How do we do observation? What is the correct way? What is peer review? How to do it exactly? So all these things are assumed, plus all the body of mathematical theories, or at least some of it. Let's not take the entire warehouse of mathematics. At least some of it that you really need, you already assume it for free. You don't go negate. You know what? Oh, let me see. Is this theorem that P is congruent to Q whenever PQ divides N? Is this valid or not? Oh, this is the mathematician's job. Let them check for the validity of that. I'm just going to use it for my own advantage whenever I need it. I've never heard a physicist say, oh, we're going to start questioning the proof of Hilbert spaces, whatever. Oh, no, they just take it and then they use it.
Well, we
They
don't
just take
ever
pi equals 3 and they don't care. That's what.
we don't
So,
ever worry that the mathematical part of what we do could be fundamentally wrong, in the same way that we know that the thing we're doing the math about could easily be fundamentally wrong.
well, I think it's as easy to make no sense with math as it is to make sense with math. It's just an expressive language. I can make sentences that have meaning. I can make sentences that don't have meaning. So I don't know what it means when John says they don't worry about getting the math right. I think people ought to be more worried about getting the math right.
No, and once again, I'm not talking about fallibility. I'm just saying that as physicists, we don't. Maybe we should more often. We do a proof. If we do the proof right within the model, right? We have a mathematical model. We can do proofs inside that mathematical model, and if we do that correctly, if we don't make a mistake, then the thing we come up with, we can test to see if it comports with reality. We don't
Well,
ever
I'm
work.
about your word because language suggests you get a Boolean result. In a proof framework, a thing either is or isn't. Um, but reality is rarely our confidence in our on our physics product is rarely Boolean. So when you say a physicist is using a proof, I'm worried already that he doesn't understand what the hell he's doing.
Well, I mean, once again, just remember, I'm saying we can do literal mathematical proofs within the model, which is a mathematical model of reality. It's not reality, it's a model
It's
that
that
we're
last
mapping
of
onto
reality that
reality.
gets you into trouble. Said, look, if you wanted to prove that the Earth was a globe, you would fail, right? The Earth is not a sphere,
Right.
right?
Well, okay. Oh,
That's
that's
what I'm
what you're
getting
saying.
at,
But I mean,
right? Like
I can,
reality
but I don't have
is
to.
you need to you could say something like this. The Earth is conformant with a sphere to 3 nines, right?
Right. And I don't have to
99.9.
prove that. I don't have to prove that because I have something much stronger than a proof. That's a directly observed fact.
Well, the conformity of the Earth to a sphere is not directly observable. It's very difficult to work out. Some people are aware that the poles are, for example, wider than the North Pole. I doubt you could even describe how to work that out, much less. I don't think you could work that out if I gave you $1 million. I don't know what you'd do. Would you hire an airplane? What would you do if you had a million
Yeah,
dollars to actually measure the
it's
shape of the Earth?
true that, well, you're certainly it's a directly observed fact that the Earth doesn't bulge out anywhere by 100 miles, right? I mean, we can take pictures of the Earth from, from geosynchronous orbit or anywhere else and prove by direct observation. I shouldn't have said proof. We can directly observe the fact that the Earth does not bulge out anywhere by 100 miles, maybe 10 miles, probably a mile, bulging out if you localize that. But once again, I mean, I think it's really important to understand that there are directly observed facts. They're used to generate more general models, and then those models have entailments in the form of other things that should be directly observed facts, which we then go out and see if they are.
So there's one more point of claimed difference between the two methods. First of all, we said certainty, deduction, collecting data, abstraction, using logical rigor, aiming for general case or specific case theorems. Turns out all of these things, when you particularly take care, in the understanding the meaning of these claims, and then checking out whether they check out or not, turns out that they don't. It's not the case. The final point I would like to talk about is another point that also Feynman raised in that clip, which is that mathematics considers any hypothetical situation at all, only limited by imagination, which is kind of what we're talking about here and there in the discussion that we had earlier. And then physics, on the other hand, only cares about one world, just one world, one specific world only, which is the objective, real physical world that we exist in and experience. So science believes this physical world exists. Science believes it has access to it. And these assumptions we're going to talk about later, of course, when we tackle more directly the contents of the scientific method, because you can't open a physics books and read those. They don't. It's not like it's the front page. It should be, if you ask me, but it's not. So it's worthwhile discussing them. That world, that one physical world that we all live in and we have access to and we can understand, is the world that physics is concerned about, not any other world, just that specific world. Not many worlds, not infinitely many like in mathematics. Mathematics is not concerned. You can construct whatever fictional, imaginary world you want to think of. Kind of entails some Platonic kind of ideas, but whatever, this is not our discussion for today. Let's see if this checks out. I have this example here on slide 15. A mathematician and a physicist, two people, they try to discover the length of the hypotenuse, so the biggest side of this right triangular field. It's a real piece of land. It's out there in the real physical world that we can go and measure. So what does the physicist do? Because he does not care about all the imaginary different worlds. The physicist goes, takes a measuring tape, the most precise one we have, right? The most precise measurement tool. You want to take a laser, you want to take a surveying tool, whatever, for simplicity, right? Imagine this. And then goes on measuring the first side A. Turns out it's between 0.9 and 1.1. Of course, there is an error because he's measuring with, a physical object. And whatever this physical object it has, those properties, it kind of dilutes. It's kind of with temperature. There's errors in measurement that you can think of, and probably people who are more specialized than me in physics can tell us all about these different kinds of errors that physicists are well trained to measure and quantify. So there's an error in this measurement. Arbitrary, right? Imagine with me, it could be more specific, less specific. For simplicity, I took between 0.9 and 1.1. Okay, whatever unit you want, meters, kilometers, whatever. B as well, same thing. And then you measure C, and it's between 1.3 and 1.5. This is the result that the physicist got. And then he goes to the mathematician. He's like, this is what I got. And then the mathematician had a different thing going on, because the mathematician is thinking of imaginary, abstract, right? Infinitely many worlds. The mathematician takes the measurements that the physicist has done for sides A and B. Because there is no data, the mathematician has to have some data. He can't start, or she can't start working on the problem with zero information. In mathematics, we all know that you have to give us the given, give us the axioms, give us the hypothesis, give us something that we can use. So he takes the measurements that the physicist has made, and whichever method the physicist is happy with. A is between 0.9 and 1.1, B the same way. And what does the mathematician do? He uses Pythagoras' theorem to calculate a lower bound for the side C and a higher bound for the side C, which happens to be, in this case, if you do the math, between 1.27 and 1.56. If you do the rounding, you will have very, very similar results to what the physicist got by direct measurement of the real, actual, 100% flesh and blood, one universe that we live in. The question is, which one of those two is only concerned about one possible unique world, and which one is concerned about infinitely many? This is the real question. Because if you were going to accuse the mathematician of being concerned about infinitely many worlds and infinitely many possibilities, I will remind you that those errors that the mathematician had, those errors were due to the physicist's errors in his measurement. If you had given the mathematician A equal 1 and B equal 1, the only answer that the mathematician would have got was the square root of 2. The one unique answer and the one unique situation that we have here in the unique world of Euclidean geometry is the square root of 2. That's only one answer, one specific world where this is the case. Whereas in the physicist world, this could be anything between 1.3 or 1.5. Exactly how many? Infinitely many. Uncountably infinitely many, not only infinitely many. So can I keep accusing the mathematician of not caring about so only caring about imaginary worlds, and the physicist caring about this is a situation where originally the way I wrote this example was the following. I said Bob and Alice are two. One of them is mathematician, one of them is a physicist, and then I will ask the audience who is who. But then I was afraid that people say, oh, but a mathematician can think like a physicist, and a physicist can behave like a mathematician, and then we kind of lost in that thing. So I rephrased it, but the point stands. Can we really tell the difference here between the two? Only by looking at the point of who is it that is considered about many worlds and who is considered about only unique answers and very accurate answers. It is the mathematician, in fact, if you want to hold that criterion, it's the mathematician who cares about the precise, unique answer, whereas the physicists are happy with having errors, either in observation or in results. And when the mathematician gets the data from the physicist, they use it to get very similar error margins. Yes?
I don't know that this matters. Yeah, I don't know that this matters at all to what you're saying. I'm not sure I wrap my mind around it completely. But I noticed that for some reason, the mathematicians decided to take the two sides as being, in some sense, more certain than the hypotenuse. I mean, if they could have made another choice, and they would have found that the sides should be somewhere between 0.7 and 1.2 if they'd
would
done
that
the
be
other
the
way
case?
around.
How would that be the case?
They'd do just what they did, but they'd start with the hypotenuse measurement in one of the sides and then calculate what the range for the other side could be given Pythagorean's theorem.
But then you have to ask the physicist to do the same. So now we're solving two different problems.
No, but the physicist just measured it. I mean, you just said,
yeah. You just measured them. Okay, so your point is if we had A and C and then we want to calculate B instead of A and B and we want to calculate C?
Right. I don't know that it makes any difference for what you're saying, but I don't know why the mathematician decided.
Do you see a difference? In my mind, it's the same. We can flip the problem and then we can still get Again, the point of this exercise is to question whether mathematicians care about infinitely many worlds all the time, and we can imagine whatever we want, and then we can create whatever theory we want, and we can modify it whatever we want. This is the kind of general naive view. Whereas the physicist only cares about one unique situation. In this case, the person, it's kind of clear to me that the person who really cares about the unique answer to the unique situation is the mathematician. Whereas the physicist, between the world that this is 0.9, 0.9, and between the world that this is 1.1, 1.1, there's infinitely many worlds that could be the case. So if you want to hold science to say, oh, science only cares about one universe, I will remind you that one universe is described within your theory using those observations, using that mathematical language, and that observation is encoded with errors all the time. And whether it and since it is encoded in errors all the time, you're getting a collection of worlds that you're dealing with all the time, not only one universe. This is the point.
Right. I mean, in truth, I mean, this would be very similar to the kind of thing I would have students do in an introductory physics lab. Do something like this, and then see if their measurements if their measurements comport with theory, which in this case would be Pythagoras' theorem, or not, right? See, in other words, whether their measurements are within the tolerances that they estimate their measurements to be within. And so they would proceed to do something like what the mathematician did in this case, but something I think a little better, in the fact that they would, for instance, they'd take A and B, square them along with their uncertainties, and see what the range of possibilities for the hypotenuse is. See if their measurement comports with that, in the fact, in a sense of a sigma thing, right? Did the So they take the difference between the square of the two sides and the difference between the square of the hypotenuse with uncertainties, and see if those two things agree within the propagated uncertainties that are associated with their measurements. And they would find in this case that
I see.
it does
Yeah.
so well that in fact they must have I use this kind of an example to prove to them that they must have overestimated their uncertainties, because the two values agree far too well given the uncertainties that they assign. That's kind of an important thing too. In the case that you've used here, you have clearly assigned far too much uncertainty to the sides and the hypotenuse.
Oh, yeah. I see your point now. I kind of misunderstood earlier. Yeah, absolutely. So there are many ways, and again, this is something I alluded to earlier. There are many ways to deduce that error. There are many ways to make better measurements. Of course, absolutely. If this triangle was under a heat source, you cannot use any physical way except like a measuring tool or a rod or whatever. You have to use lasers. This is the best. There's different ways of measurement for different situations. And of course, exactly whatever you're saying. And this is an excellent point. I have kind of cheated a little bit by using a very elementary way of calculating here, using a better way of calculating with not taking those steps, but taking different route towards the calculation, could have ended up being a lot closer. That's not exactly to the point, though. The point is going to the many worlds and interpretation versus the very single one unique universe. Whatever you do, right? Even you, and of course in science we can get to +5 standard deviations, +6 standard deviations in measurement. This is 99.9999998 something %. This is incredibly accurate. And when you think of this, they can do this in particle accelerators like the LHC. It's like 5 standard deviations. Do you know how accurate you have to be to get your answer up to 5 standard? This is incredibly accurate. Still, we are talking about technically infinitely many worlds. A sort of. Let me go to the second slide. Maybe this makes it a little bit easier. So even when we assume that it's not our error. So something kind of Hansen alluded to earlier, it's like we are stupid. Okay, we are stupid, fine. But we kind of know now, and this is a great here link to John's series on quantum mechanics that he did a little bit earlier, like 2 weeks ago, fully on YouTube, hopefully by the end of this week. The Heisenberg uncertainty principle shows that there's an inherent, unfixable, so far, unfixable error in measuring of the physical properties of the particles. I say so far because there's always, every once in a while, a research paper that says exactly what John says. By doing a series of very light, undisturbing measurements, there's a way to reduce the error less than the Heisenberg uncertainty. But then, I don't know. What do I know? I trust the scientific community. I wasn't in the lab with them. I will follow whatever they say. So I don't know. I have no clue. But so far, the established and the accepted thing is that this is unfixable. You can, whatever you do, even if you do series of very sensitive, very undisturbing light measurements, then you will get to a smaller error, but still an error. So we are locked. It's a property of nature that we will never, as physicists, we will never be able to deal directly with nature itself. John will be happy now. We will never be able to be indirect with nature. This claim that physics only deals with one world, this is just hallucination. You are bound as a physicist to deal with a member, one member, you choose it, of an infinite bounded class of quote-unquote toy worlds that are with double asterisks coupled, because I've never used that word before, and this is what we will use to talk about meaning and truth and later on, etc. But in some very naive way, those toy worlds that we have are coupled, they are connected with quote-unquote the real one. This is the final table that we have here. Again, when we think of math, we assume certainty, we assume deduction, we assume abstraction, we assume logical rigor, we assume the aims for general case theorems, right? So we want general, not specific, and we assume no hypothetical. We assume only hypothetical situations. You can imagine whatever world you want, whereas in physics it's the other way around. These points do not hold. Now, in conclusion, maybe those conclusions don't directly follow, but what I'm hoping to allude to by this conversation, by this presentation today, is the following. If we're gonna get rid of whatever is on those differences, whatever has a red X next to it, because we kind of shown this is not the case, you end up with the following table. Math and physics both are not certain. Both use deduction and induction and other forms of abductive reasoning. Both collect observations about concrete, material, physical systems. Both mathematics and physics. Of course, number two does not grow on a tree. Of course, you will not run into pi walking on the street. But it is nonetheless a physical object, just like we saw with the twin prime conjecture. You are looking at the list and you are verifying whether what you have in mind is the case or not. This is exactly the same thing. When I imagine it in my head, you have a picture in your, it's a mental picture, it's an imaginary picture of the list with the numbers. Okay, same thing. This is a very physical thing. Are you going to be, only a dualist can say, oh, this is not. The spirit kind of thinks in a different way. This is outside of the physical world. Fine. But as long as you're not a dualist, then the imagination of something, the picturing of something, the writing about something, the description of something, and the thing itself, of course, they're not identical, but they are both very, very physical in nature. And so when I say, oh, one of them is abstract, what is abstraction? Abstraction is only, again, with double asterisks, a connection between two physical systems. There's a physical system on the computer, and there's a physical system out there. I have a model, quote unquote, of what's out there on the computer, or on my paper, or on my tablet, or in my imagination. This model is physical. Those equations are physical. That description is physical. And the thing happening out there in the world is also physical. They are of the same exact level of reality. Both mathematics and physics, therefore, have to build, quote unquote, toys that model their claims. There's a toy that is my drawing when I'm drawing the right triangle. This is not the right triangle that Euclid describes. The right triangle that Euclid describes has lines that are infinitely thin that I cannot see. This is just a representation. It's a toy of it. And I accept it as identical, or at least similar. Why? Because I have a certain coupling. Again, I go back to that, but don't ask me about it. This is hand wavy because we haven't shown on what basis you can make that. Because you can always find the coupling, right? One-to-one correspondence you can always find an n-to-one map, and then you can say this is the case. So on what basis do we have it? Can we just any function? This is a different discussion. But we all understand and agree, hopefully, that whenever you're building this toy model, whether it's in mathematics or physics, what you are doing is making a coupling between that and what's out there. And this is where you do your work. Physicists uses the word model, so this is a model in the sense that I just used it. Mathematicians, as I explained in the logic episode we did, it's the other way around. We say the theory is modeled by that toy. Whether you want to use it in this sense or the other sense, there's always a toy, and there's always what's out there, and there's a coupling between what you have here and what you have out there. And this is how you're doing your work. Both of them are physical. Both of them depend on your action, your observation, your analysis, your participation. And they are both not certain as a result. Now, I see Wissam in chat typing, this is not enough to prove that these two are identical. I want to address that in a minute. Whenever I want to prove, naively speaking, because I don't understand here what you want me to prove, this is a meta-theoretical proof now. I need to have a framework, a set of axioms, so that I can do my proof. So now we're gonna have to agree on those axioms, whether you agree with them or not, and then we're gonna see whether they fit whatever it is that we want to do. Naively speaking, whatever I have in mind, right, is that if you have two sets, okay, so this is mathematics and this is physics, I'm claiming that they study the same thing and they work in the same way, okay? Because whatever it is that's happening here is also happening here, and whatever it is that is not happening here is also not happening here. In my mind, this should do the trick. Now, how is it that you can tell me this is not the case? This is missing, this is misleading? By finding something that mathematics only does, okay, which physics cannot do or does not do. So is mathematics something abstract? This is how the conversation kind of happens in colloquially, right? People, oh, mathematics is abstract, so physics is real. Mathematics is induction and deduction. They count all the different and say, oh, they are different. Those basic, let's say, descriptions that people believe, we showed that each and every one of them is not the case. There is no difference as far as not only me and you, but apparently one of the leading scientists, Richard Feynman, has in mind about math and physics. Is this a proof? No, but not, by no means this is a proof. But again, the requirements for a proof are not even here. What axioms and what derivation rules am I going to use to establish that those two domains are the same exact thing? I'm not sure. We can probably come up with that theoretical framework. I don't know. I don't have it in mind. This is totally not a proof. This is just negating whatever it is that people have in mind, whether they are lay people, people who are vaguely interested, or people who are absolutely in the domain. We brought those points of views and we kind of described them. So yes, absolutely. If you're waiting for an accurate, exact, deductive proof, I don't even know this is possible to provide. If you can just let me know if this connects to whatever you have in mind, or does it sound like I'm dodging the question or whatever. But I thought to address it because this is an important point. I don't think that we can do these kind of proofs until you have the theoretical framework, and I don't even think it is necessary, to be honest with you. If only my goal here today is to negate those 5 or 6 points, and if you accept with me that I have done them, I'm a very happy man. If you can find other points where they differ, please let me know, and then we can talk about them in chat. Thank you so very much for being here today. I'm done. This is the presentation entirely. So now the floor is open for your questions, your comments, other discussions you want to have. Please go ahead. Thank you. All right. So let me address Wissam's point pretty quickly here. You seem to think that since ideas have physical realization, that those ideas refer to those realizations. They do not. The point is that mathematical ideas often refer to entities that do not exist in the domain of physics. I can take either position on this one. I can tell you, okay, as you say, mathematics does not refer to entities that exist in the physical world. Although I hold the opposite point of view, but I can walk with you on this one. I hold the belief, if that is the case, that also physics does not refer to objects that exist in the physical world. If this is the point of distinction you want to draw. Physics, when it talks about What is this joke, you guys? John, let's assume the cow is a sphere. Is this like a running joke whenever you're learning about magnetism? We always make these simplifications every single time. You cannot. There's no way that you. It's not only because we are stupid or because our computational power is not enough. If you want to encode every single property about the particles out there to study them, then every property will need at least one particle to encode for it, right? And since every particle has many properties, you're going to need more particles than the particles you have. The objects you have in your physical theory are not, by that, cannot be encoded, all of them physically, cannot be represented physically. So if you're going to hold the fact that mathematics refers to non-physical things, physics also refers to non-physical. You don't like that that explanation. Let me give you another example. Something a little bit easier so that we don't get lost in the details. You're doing statics. You want to see whether a certain swing balances or whether you can this pendulum, where does it, etc. Statics. The simplest way, the way that we learn, the way that every student learns how to do it, is by referring to something called the center of gravity of an object. One of the forces that this object is subjugated to, at least when we're dealing here on the planet Earth, we can naively think of this as a force, and then we can say, okay, there's the gravity, and there's g, and it's an acceleration, 9.8 meters per second square, etc. And then we say, for something to be balanced, its center of gravity has to be so and so, according to the situation. But what is the center of gravity? Is this a physical entity? Is there an atom somewhere that I can hold and grab at the center of that object and say that is the center of gravity? No. In fact, even if you pinpoint that exact point, sometimes it could be between two molecules, between two atoms, but assuming it is that particle, and you remove it from the object, guess what happens? That center of gravity is still there. Is that a physical object? No. Our physical theory, our best physical theory, whenever I'm doing that example, statics, right, it refers to something that is not physical. What do you want to do about that? And if you want to hold the other point of view, that mathematics refers to things that exist physically, which is the point I kind of believe myself. So number 0 and number 1 and number 2 don't grow on trees, but they are physical entities on your paper or on your computer, on whatever it is that you're using to do that. Then by I don't want to say entailment here, but also, moreover, whenever you use these objects in your physical theory, guess what you're doing? You're using objects in the real world that are physical to express physical facts about the physical world. So they go hand in hand. If you want to assume that mathematics refers to some things that are not part of the physical reality, also physics does. And if mathematics doesn't, then physics doesn't. That's how I see it, by the way. And please let me know if this convinces you or not.
I really have been thinking about, especially since you put that Pythagorean theorem example up, one thing that's really is critically important, it's really central to all science, is uncertainty, right? That we, in our mapping of our toy models onto the real world, we have to cope. And this is really the biggest thing we cope with, bigger than our theories, bigger than anything else, is what to do about the fact, about the unavoidable fact that all measurements have some uncertainty. And you have to somehow figure out some way to figure out what that uncertainty is. And it's really critical, right? I want to say, well, what if I have two objects that have this mass, I measure their masses, and now I put them together and I measure their total mass. Is the total mass the same as the sum of the two masses? And it isn't. But most of the time you'll measure it to be the same with an uncertainty. You'd have to, and no matter how many times, no matter how much better your measurement gets and assures you that they are the same, You can never know that because there's always going to be uncertainty. And I'm not talking about quantum mechanics. I'm just talking about the fundamental fact that all measurements have some instrumental uncertainty. And so, we do know that it is the case that when you measure the mass of both particles, you put them together and then measure them, it won't be the same. But you have to have real precise measurements to notice that.
Yeah, absolutely. Absolutely. The point here is that I think everybody accepts, that science has those uncertainties. The point, the mistake that people make is that mathematics has certainty, as if it is, given by some higher dimension or by some higher beings, that can do and infallibly do things, or given by some god above and beyond the physical universe. So yeah, absolutely, it's the other way around that people make the mistake. Which brings me to the conclusion of today. I have to close because it's getting late for me, and my neighbors could call the cops. In the real physical world, the actual cops are going to come to me. So I have to stay off duty now and acknowledge that, yeah, the actual physical universe is coming to get me. Thank you so very much for everyone who was here today. Hansen, John, Wissam, everybody else, Mind Virus coming here at the end. Thank you all so very much for being here.
I just you wanted to say I'm usually in the audience lurking while I work in lab, but I just wanted to say I really appreciate these rooms that you, Shamash, John, Sam, Ben have been running. I was really excited when the scientific discourse stuff booted up. I feel like the app is in great need of this kind of content, so I really appreciate not only the quality of the content you guys are generating, but the consistency, which is what makes all the difference. So I really wanted to thank you guys for everything you're doing, and don't take my presence in the audience and not on stage as a lack of appreciation.
Oh no,
Thank you.
not at all. But the same thanks go back to you, sir. I also lurk in your rooms on Sunday afternoons. Uh, and please don't take my lack of presence on stage as an offense in the same exact way. Usually I'm doing something else, and that's why I can't be present, but I highly appreciate what you do as well, which is slightly different. You take the actual paper and you have the link and you have people read it, which is also something this app and this space really misses and really needs. So highly appreciate it to you. What's the name of the house that you opened, Wissam? Can you tell us the name again? Is it not? It's not the consciousness one. It's the other one, the Gödel one,
Neurophysics.
right? Yeah.
I do read in another house called Gödel's Parallax, where we read
Yeah.
like philosophy of physics stuff. Yeah. But neurophysics is the house that I run on my own. Yeah.
And when do you have your weekly rooms, so that people know?
I used to be really consistent. Like I would do a Wednesday room every week. I would do a Sunday room every week. And now I'm just really busy. So I try my best to do at least a Sunday room and sneak in things during the week. That's as good as I can do. So that's part of why I was, applauding your consistency with these rooms, because it's really nice to know this is going to happen
It's good
Wednesday.
to know I'm not the only one in a laboratory.
Yeah.
I'm making my perfumes all the time. I make perfumes in my laboratory. That's when I'm on Clubhouse.
Nice. Anyway, people, give Wissam a follow, give John a follow to stay updated to their activity. Join the house, Philosophy Wednesdays. The links will be in the chat in the next 30 seconds. Join the YouTube channel, the Scientific Discourse YouTube. Just search Scientific Discourse, you'll find it, where I will try my best. Working full-time is a mess, man. I'll try my best to edit and upload those rooms that we do on a weekly basis, so that if you miss something or you want to watch it again or hear it again, it'll be up there for your reference. Thank you all so very much for today. Wonderful, wonderful place to be. You guys are the voice of sanity in my life. Take care and Merry Christmas.